incredibly intimidating, dense algebraic topology, and translating it into a tool that literally maps out the hidden shapes of stories. You know that intuitive feeling you get when a document tells a straight, linear story, while another one twists, turns, and brings you right back to where you started? Well, what if we could actually measure that? What if we could mathematically prove the geometry of a narrative? So what exactly is the shape of a story? Let's dive right in. Imagine a document's paragraphs as dots floating around in this multidimensional space. If we connect them chronologically, drawing a line from the first paragraph to the second to the third, and so on, what does that curve actually look like? If an essay has this really satisfying conclusion that ties directly back to its intro, does that curve fold in on itself and form a measurable loop? To measure these narrative loops, we use an algebraic method called persistent homology. Now, unlike traditional text analysis that basically just counts words, persistent homology captures novel structural features in the data. It looks at our point cloud of text at multiple scales to pinpoint clusters, actual loops, which are called first-order holes, and even complex multidimensional voids. It's kind of like finding the architectural blueprint of the text. To truly grasp this, we're taking an interdisciplinary journey today. We'll start with the shape of a story, move into the mathematics of the rubber band, check out the algorithms for text topology, apply it to the math of nursery rhymes, and finally, look at how writing actually grows up. All right, part 1, the shape of a story, where we treat paragraphs as point clouds. Let's see how this builds our foundation. Going back to our point cloud, if an essay just jumps from one distinct idea to the next without any tiebacks, the mathematical curve it draws never forms a hole. It just stretches out forever. But a really good essay that circles back to its thesis, where the start and end share deep semantic similarities, that actually creates a measurable topological loop in that multidimensional space. Those semantic tiebacks are exactly what we're looking for. Moving on to section 2, the mathematics of the rubber band. We need to introduce the math to find these holes in space, but don't worry, we're going to use a super relatable analogy. Imagine our space is this yellow area, and that white circle right in the middle is a hole. Homology finds holes by grouping cycles. Think of these cycles as rubber bands. A blue rubber band can stretch and bend to become the green one perfectly fine. They're totally equivalent, right? Neither surrounds a hole. But you absolutely cannot stretch that green rubber band to become the red one without tearing it. Why? Because the red one is looping around that white hole. So homology uses algebra to separate the uninteresting rubber bands from the ones that actually loop around a meaningful gap. The thing is, rubber bands are continuous, which makes them really tough for computers to calculate. To make our text data computable, we discretize the space using things called simplices. These are basically the geometric building blocks of our document's shape. We start with a 0 simplex, which is a single vertex or dot. Connect 2 dots, and you've got a 1 simplex, an edge. 3 dots make a 2 simplex, a triangle. And 4 dots, that gives you a solid 3D tetrahedron, a 3 simplex. It is honestly fascinating to watch how a single isolated idea, just a dot, progresses into a fully connected, multi-dimensional structure. By grouping our text data into these geometric shapes based on how similar the concepts are, we can actually build a discrete mathematical space to analyze. Okay, section 3, algorithms for text topology. We've got our mathematical rubber bands, we've got our building blocks, now we just need to connect the dots. The researchers tested out 2 different methods here. The first is SIF, or similarity filtration. This one is pretty simple. It groups text units purely based on how similar their vocabularies are, totally ignoring the order they actually appear in the document. Then there's SIFTs. That stands for similarity filtration with time skeleton. SIFT adds a really crucial extra step. It first connects the text units in chronological order using a time skeleton to map out the narrative flow, and then it looks for similarities. So why does this matter? Well, the crucial takeaway here is that by adding that chronological time skeleton right up front, SIFTs can actually detect when a narrative has looped back on itself. Because SIFT ignores the text order, it basically just fills in the space with solid geometric triangles as sentences become similar, which completely prevents true narrative holes from forming. SIFTs, on the other hand, preserves the chronological journey, and that allows those semantic tiebacks to form a ring, a mathematical hole right there in the data. Section 4, the math of nursery rhymes. I know that was a lot of abstract algebra, so let's apply this high-level math to something inherently simple and, well, silly, just to prove it actually works. Think about the itsy-bitsy spider. The first sentence has the spider climbing the spout. Then comes the rain, then the sun. Finally, the fourth sentence, the spider climbs the spout again. When the spider climbs up the spout that second time, it creates this powerful semantic tie back to the very first sentence. And guess what? The math literally proves it. The persistent homology barcode for this rhyme, which is basically a graph mapping the lifespan of these geometric shapes, uses that SIF's algorithm to prove without a doubt that a narrative loop is born. It gives strict mathematical weight to the spider's cyclical journey. Conversely, let's think about row, row, row your boat. You row your boat gently down the stream, merrily, merrily, life is a dream. Now that is a completely linear progression of distinct ideas. It never loops back semantically. And just as you'd probably expect, the algorithm correctly detects absolutely zero holes. The math perfectly matches our intuitive understanding of the story's shape. Pretty cool, right? Which brings us to section 5, how writing grows up. Now that we know the algorithm works beautifully on simple nursery rhymes, let's look at the real-world data reveal. 17.6. That is the staggering average number of topological holes found in the essays written by adolescents in the study. Let's look at how that compares to the younger writers. The data reveals a truly profound difference. Only 87% of the child essays contained any geometric holes at all, and they averaged just 3 holes per essay. But the adolescents? 100% of their essays contained holes, jumping to that massive 17.6 average. And get this, even when researchers truncated the older students' essays to match the exact length of the children's essays, the older writers still produced significantly more topological loops. So older writers don't just use bigger words, they actively construct significantly more complex, looping geometric structures in their arguments. Now, you might be sitting there thinking, wait, doesn't this just count repeated words? Like, if a student says the exact same thing 3 times in a row, does that generate fake narrative loops? The answer is no. The math fundamentally ensures we are measuring the true geometric structure of the narrative, not just simple repetition. And here's exactly why. If a concept simply repeats back to back in contiguous sentences, the algorithm merges them into a solid geometric shape, a kind of superunit filled with triangles. That completely avoids the false detection of a narrative loop. It genuinely requires the story to venture out into completely new semantic territory and then intentionally return to a previous point to register a topological hole. To wrap up this explainer, I want to leave you with this thought. Right now, large language models are incredibly good at predicting the next word. But by using persistent homology, we can actually give machines the ability to mathematically see the overarching structural geometry of our writing. If we're already capable of mapping the topological shapes of our stories today, what entirely new dimensions of text comprehension, automated editing, and artificial reasoning will AI unlock next? Thanks so much for learning with me today.